Welcome to another exciting computer architecture class. Um, let's see if we can review a few dates here today. We have a homework 11, which is due tonight. And hopefully you guys are all set with that at this point. So we shouldn't have to go over it unless there are some outstanding questions. Are there any outstanding questions about homework 11? Hearing none, I'm going to move on to the next order of business, which is the final. I don't know if you've noticed, but the final is out and you should have access to it now. And if you don't, you have to tell me. The final is due at the end of the day on the 17th of December. And please do not wait until the last minute to submit the final. It is multiple choice, Blackboard graded. The deadline's enforced by the computer, and it's the end of the semester, so we can't be late submitting it. It counts for 1/3 of your grade. It has 100 questions. 100 is a nice round number because if you assign 1 point to each question, it all adds up to 100. So that's nice. Now, that means that some questions which are hard are still worth only a point. And other questions which are easy are also worth a point. So everything's worth 1 point, whether it's hard or it's easy. You probably could print the whole thing out if you were so inclined, and then do it offline and mark it up, and then just keystroke the answers in. That might be a thing to do. You've got 2 attempts, and your score will be reflected on the highest of the 2 attempts. So that's the shtick. And we'll cover some of what's on the final, but outside of that, are there any questions about the final? No questions? So it's open book, open notes. Please try to work on your own. You have 2 weeks in which to do it. It shouldn't take you 2 weeks to do this. It's all multiple choice, really. There are a lot of true false, too. And what I can do is slowly go through the final and sort of ask if anyone has any questions. What do you think? Would you guys like to take a stab at answering question number 1? Given the following code, thread T equals new thread, T is now ready to run. Is that true?
False.
That's false, right? It's not ready to run until you do a T.start. That's the key. So you do T.start, and it's still not running with T.start. It doesn't run until the thread scheduler allocates some resources to the thread, and then it will start to run. A host that is configured to receive datagrams sent to a multicast address becomes part of a multicast group for that address. Yeah, I don't know. What do you think? Does that sound true or false?
Is it true?
That is true. It is true. So in other words, the group is receiving all of the datagrams at the same time. It's a broadcast medium. In fact, if you think about it, Ethernet is a shared medium. And when someone broadcasts a packet, every other interface message processor can receive it. So that is true. Let's look at question 3. Oh, pictures. Here's Amdahl's law. So this says 95%. This says 90%. That says 75%. And this says 50%. And this is the parallel portion. So if the parallel portion is 95%, and you put in 16 processors, you only get a 10x speed up. If the parallel portion is, let's say, only half, of the application and you put in 16 processors, you only have a 2x speed up. So in other words, it asymptotically approaches 2x because only half of the job is parallelizable. So there are diminishing returns in adding lots of processors to a single job unless you can make it an embarrassingly parallel program. That is, you'd like it to be 100% parallelizable. And if the entire thing can be parallelized, then if you add 16 processors, you should get it running 16 times as fast. But usually there are things that are sequential, like I/O. So here's the latency, and that is equal to 1 over 1 minus p plus p over s. In Amdahl's law, the p stands for the proportion of the execution time that the part benefiting from the improved resources originally occupied. S is the speed up of the part of the task that benefits from the improved resources. S latency is the theoretic speed up of the execution of the whole task. Does that sound true? What do you think? So let's think about this. S is the speed up of the part of the task that benefits from the improved resources. So you could speed up by, I don't know, 16, the part that is parallelizable, but if that only represents 50%, right? Where would that go? The proportion of the task benefiting from the improved resource. So that's 1 minus p, that's 1/2, plus 1/2 divided by, let's say, 16. So that's perhaps 8. And then you have 1 over 1/2 plus, what 8 or something, 1/8. So I don't know. It doesn't seem like this is going to improve things a whole bunch for the blue line. Any ideas? Latency is the theoretical speed up of the execution of the whole task. This is straight out of your book, and it is true. That is true. So you're basically looking at this sort of law of diminishing returns. The proportion of the execution time that is parallelizable. You could say it that way. Let's see now. The Arduino Uno uses the von Neumann architecture. Von Neumann architecture, what's that? What does that do that? What is that? Computer architecture folks here. Well, let's see. Angelica, what do you think?
Is it true?
You know, it isn't. And the reason why is because the Arduino uses memory for the program that is separate from the memory for the data. It uses a so-called Harvard architecture. The von Neumann architecture has memory which is shared by both the data and the program. And the reason that you have separate instruction memory from data memory is because the instruction memory is available as soon as the computer boots. That means that for the microcontroller, you don't actually have to load the program in from a hard drive. It's already present in non-volatile memory. So you can lose power, and as soon as the microcontroller comes back on, it starts doing whatever it's been programmed to do. So if you've got a microcontroller in charge of your dishwasher and you turn off the dishwasher, as soon as you turn it on, it comes back with the dishwasher program, whatever that is, illuminating the front panel and getting ready to accept times and cycles and things like this. Well, all modern dishwashers, I think they're almost all digital now. They all have computers in them. And so you really want an embedded microcontroller where the program resides in the non-volatile memory. So here is, let's see, question 5. It says here, a cache is a smaller, faster memory closer to a processor core, which stores copies of the data from frequently used main memory locations. Most CPUs have different independent caches, including instruction and data cache, which kind of makes them sound like Harvard architecture right there. So let's see, Avery, what do you think about that one?
Is that true?
Yes, it is. That is correct. So so locally, the cache for instructions should be different from the cache from the data, because you'd like to have the cache for the instructions sort of prefetched and ready to go in a sequential memory location. So that is true. CAM, this is content addressable memory, compares input search data tags against a table of stored data and returns the address of matching data. Let's see, Bashir, what do you think of that one?
True.
Also true. Yes, that is true. And that's used for virtual memory addressing. They have the tables. Let's look at question 7. A company will only warrant that their double EEPROM will work to retain data for 100,000 writes. Thus, it will automatically fail after 150,000 writes, right? Let's see who we can talk to about that. Beatrice, what do you think? Beatrice Guevara? Are you there, Beatrice? Let's go to Caroline. What do you think, Caroline?
Is that true?
You know, it isn't, because the memory could easily outlast the minimum warranted number of writes. So it doesn't have to fail immediately after 100,000 writes. It could still work, but it might become a little less reliable. So it may be the case that it may be harmed, but it will still work to retain at least some data for a while. So that's false. So this is your Arduino, your basic microcontroller, and it has double EEPROM in it, built into the chip. But if you keep writing to it, even if it's meant to be written to for during development, like if you're developing programs and you save 100,000 programs as you go through the development process, eventually you're going to wear out the double EEPROM. Let's look at question 8. Arduino has a Harvard architecture. This is the key from before when we said it had von Neumann, with programs stored in flash memory and data stored in static RAM. There's also double EEPROM, 1 KB long. Programmers never use this. Never use this. Let's see. Beatrice, are you there? What do you think?
Yes.
You are here. Good, good. What do you think? Is that a true or a false statement?
False.
Yeah, that's false. You can certainly use double EEPROM. There is no difference between flash memory and double EEPROM. No difference. No difference. It's all the same. Let's see. Who can we call on? Who hasn't gone? Daphne. What do you think?
I think that's false.
Yeah, that is false. There is a difference. You could have NAND, which is regular flash memory, and then you have NOR memory, which is what you use for the double EEPROM. You can, with double EEPROM memory, you can read and write single bytes. Its control logic is laid out in such a way that all the bytes are accessible individually, although it's slower than writing regular flash. But the benefit is you can use it in smaller and older electronic devices. And if you look at the NAND flash, right, you have to write blocks of bytes, and you can read and write single bytes, but you have to overwrite the whole byte in the process, the whole block in the process. So it requires wiping out a lot of other bytes. So you've got to do block IO with NAND flash memory. Let's look at question 10. In the Arduino, flash memory, which is normally for your program, is used to store programs. I guess I didn't have to say normally for the program since it says that. It is 32K bytes long, of which half, actually it's probably more like 400.4K bytes, is used for the bootloader. So this is interesting, right? Because if you buy chips like the 3028P, which is what they have in Arduino Uno, and you put them on a breadboard, they don't work. Can't upload anything because they haven't got a bootloader, which means they're not sitting there listening to like a USB interface waiting for you to upload some kind of a program. So you have to bootstrap the bootloader into these chips in order to get them to even start working. We could write a program that counts to 100,000 and each time writes the output to flash memory. That should not do any harm. Is that true? Let's see who hasn't gone yet. Guilhem. What do you
That's
think?
false
Yeah, that's false. Yeah, you don't want to.
because of the memory. Yeah.
Yeah, you'll wear it out. After 100,000 write erase cycles, if you keep doing stuff like that, you'll have broken your computer just by wearing out the memory. So that's true also if you have a USB flash drive, right? So in other words, if you use your USB flash drive and you format it for your Raspberry Pi and you boot off it and use the virtual machine to swap in and out of the flash drive, it won't be long before you will have worn out your little USB key and it will be basically broken. You won't be able to fix it. It will be worn out. That's different than, for example, the SD card that they use. Question 11. Flynn taxonomy is a classification of computer architectures proposed by Michael Flynn in 1966. SysD, a sequential computer which exploits no parallelism in either the instruction or data streams. SysD. And here's the processor unit, PU. And then there's the instruction pool and the data pool. They're coming from two separate caches. And does that sound true or false? True or false? Let's see who hasn't gone yet. I have Jacob. That is true. That's just what that means. So not sequential. Sorry, it's only sequential. So let's see, what do we got? Question 12 is a very pretty picture of a CUDA core. And it says here, Fermi has 512 CUDA cores, NVIDIA CUDA cores. Must be that must be MIMD, multiple instruction, multiple data, because, well, each one of the cores is separate, can have separate instructions and separate data. But it also allows for SIMD, single instruction, multiple data, branching and looping inside of a program. But because all processors must execute identical instructions in SIMD, divergent branching can result in reduced performance. Reduced performance from divergent. Let's see, who hasn't gone? John Fee, you're up.
Is it false?
No, it's true. You do get reduced performance if you start to use this as a SIMD processor. You know, that divergent branching issue is part of what happens when you attempt to do what's called speculative execution. You're attempting to figure out how to keep all the processors busy, but unfortunately you've diverged from the speculative branch, and so you can't, and you empty out your pipeline. So that causes reduced performance. It's a pipeline miss. Pipeline miss. I wonder if I skipped anybody here. Jacob, did I skip you? Looks like I might have done. Let's see. I see a data structure. Time info. It's got network time packets, some sort of list of comments and a long delay, an offset and a return time, and details computed. This must mean that the time it takes to get the response is part of the answer. Time it takes. Jacob, what do you think?
Say true.
Yeah, that is true. In other words, you can go to the world's most accurate clock, an atomic clock, a cesium-based clock. But if you have to go through the internet, there's all kinds of interesting delays going on in terms of when you asked for the time, when you got the time back, and how you have to compute that difference in order to be able to compensate for the reported time. So yes, the time it takes to get the response is part of the answer. That's true. So now I see an interface that says interface, network time traffic protocol, network time protocol version 3 packet, and network time protocol port 123. Ah, boy, what does that mean? 123. See, Jorge, what do you think? Did I pronounce your name wrong? Do you prefer George Chulusa? You're muted. All right, I'm moving on. Kristen.
Is it true?
Yes, it is. Yes, it is. Let me get my mouse here. Oh, there it goes. So now here's one. I see that a number format is used. Number format. This is some sort of a class, I guess. And it says here it's static, which means it exists at compile time. And it's final, which means I can't override it or change it. It's immutable. And it says here number format, instance of number format class is equal to a new java.text.decimal format with this very interesting looking format. That must mean that the strings are formatted as numbers 0.00. Let's see. Jorge, are you with us? All right, how about lamb?
Is false.
Actually, why would you say that?
I just because the number format is
The number format 0.00 might be useful because, I don't know, if I have $1.10, I'd like the extra zero at the end. So it is a number. That's the format, and it'll come out 0.00 where the zeros are inserted with some sort of actual value, 1.10, for example. So that is true. That's how number format works. Gives you a fixed format number.
But it say that strings are formatted as numbers, 0 point.
Yeah, that's how they'll be formatted. That style of formatting. So in other words, it'll be in the format 1.02, for example.
I just misunderstood the question.
Yeah, they're not all going to be equal to 0.00, but they'll be formatted as numbers like 0.00. Yeah. So let's look at this now. IP multicast is a technique for one-to-many communication over an IP network. Jorge, are you back? Are you missing your microphone or something? All right. How about I don't know how to pronounce it. Huh. Rakibul. Rakibul? Is it Rakibul? Are you there? All right, we're moving on. How about Ricky? What do you think, Ricky?
Yep, that's true.
Yes, quite so, quite so. Let's see now. Oh, this is a long one. Let's see. An interrupt that is generated by a timer is said to be asynchronous with respect to the CPU. And then there's this picture here. And what are we looking at? I got some RAM. I got some ROM. I got a bus controller, a central processing unit, some I/O ports, serial port, a couple timers, counter inputs to the timers, interrupt control, external interrupts. And what's the question again? An interrupt that is generated by a timer is said to be asynchronous with respect to the CPU. Asynchronous with respect to the CPU, true or false? It's an interesting question. Let's see who hasn't gone yet. Shamrock, what do you think?
This looks like it might be false.
Well, they say that it is true with respect to the CPU. So in other words, we can have timers that have these counter inputs. They can count based on some sort of an external control input. So I could just push buttons, and when it counts to 10, it just interrupts the CPU. So the interrupts can come in an asynchronous fashion. Let's move on. Well, this is about loop unrolling. Loop unrolling. Let's see. I think we did loop unrolling some time ago. It says here, loop unrolling is a loop transformation technique that helps to optimize the execution time of a program. We basically remove or reduce the iterations. Unrolling increases the program speed by eliminating loop control instructions and loop test instructions. So what do we got here? A for loop that prints hello 5 times becomes 5 print statements. Now this looks very cumbersome. Is that what loop unrolling is all about? Let's see who we haven't gotten to yet. Stephanie, what do you
That's
think?
true.
Yep. That is correct. That is correct. Oh, we're making good progress here. I think we've gotten 19 questions in 30 minutes. We're doing all right. Boy, what an easy test. I should have put in more questions. That's very funny, isn't it? I know. I should have a career in comedy. So let's see. Loop fusion or loop jamming is a compiler optimization loop transformation which replaces multiple loops with one. Let's see. Here is a for loop. And here's another for loop. So that's 2 for loops. Loop fusion does not always improve runtime speed. And now here is a single loop with the two arrays combined inside of the parentheses. That seems like it should be faster. And it says here it does not always improve runtime speed. True or false? Let's see. Who hasn't gone? Racky Bull? No. How about Jorge? You haven't gone.
I'm here.
Oh, you're here. Good. What do you think?
I'd say true.
That's right. It's true. Do you think you know why?
No, not exactly sure.
So let's think about memory coherence. If you're dealing with memory that is external to the cache, then you may have to jump from one address to the next address. And we don't know where these things are residing in memory. So to improve memory coherence, it might make sense to do these things one at a time. And so in this way, I can assign the number 1 to a series of sequential addresses. And here I can assign the number 2 to a series of sequential addresses. So it's because of memory coherence that combining these two into a single loop with loop fusion or loop jamming does not always improve runtime speed. In this case, it might, because that's a relatively small number. But if that number were in the millions, maybe not so much. So that's the deal. You really have to benchmark this stuff to tell. Let's look at this next one here. Loop invariant code. So isn't it funny how knowledge of computer architecture can impact the approach that you use for programming? You know, that this idea of memory coherence isn't necessarily something you think about when you first learn how to program. But when you start to study the architecture, all of a sudden these things matter. Let's look at this loop invariant code. It consists of statements or expressions which can be moved outside of the body of a loop without affecting the semantics, that's the meaning of the program. So here's something. X equals y plus z. That looks like you could move this outside of the for loop, do the X computation in advance, and then, as a matter of fact, it looks like the X squared could be done in advance too. So all of these things can be done. So here it says, it says that this part and the X squared can be moved outside of the loop since they are within the loop invariant code. So the optimized code will be something like this. So we create the X equals y plus z. We create an auxiliary variable we'll call T1 for X squared. And then we proceed with our little for loop. And look how much more compact the for loop is and how much faster it might be. Loop invariant code motion will always be faster when done by hand. This is the part where it gets tricky. You really have to kind of read these things. Always. Now, let's see. I guess we'll go back to the top. Angelica, what do you think? Is that true or false?
It's true.
You know, it isn't, because compilers are smart and compilers will do it for you. So if you want to be sure that it's worth doing it by hand, you need to benchmark the code. This is one of those, when you read the will always part, you don't want to do it by hand if you don't have to. And if your compiler is going to make this transformation for you, and it just might, then it's much better to let the compiler do it. Then you can focus on getting your code working and readable, not optimizing it prematurely. Let's look at question 21. So question 21 says, multiple instructions operate on one data stream. This is an uncommon architecture, which is generally used for fault tolerance. This is called MISD, multiple instructions, single data. Does that sound true or false, Avery?
True.
Yeah, that is true. That is true. So that's the MISD architecture right there. And you can see the same instructions are being executed on both computers at the same time. That might be good for an avionics system, like in a moon rocket or something like this. We don't want computers to make mistakes or generate error. Computers don't make mistakes, but they certainly generate error. So DNS is an acronym for, let's see, Bashir, what do you think?
Is it a domain network service?
It's actually domain name service. That's domain name service. So if I wanted to let's say ping or ping, let's try this one. There you go. Or ping that's working. Sometimes people block ping because they feel it's an attack, a denial of service attack. But here we're doing a ping and we get something like our round trip time. And to resolve this name into that IP address, is a domain name service function. You can do that on your own machine if you create a hosts table. So here we have a list of machines with local non-routable IP addresses, which are part of my local hosts table. So if I were to ping my LaserJet, which is a local printer, it comes back with that IP address because it's encoded into the Etsy hosts table. So I can locally resolve names into IP addresses. So that is a very old service and a very important one that we have come to rely upon. Let's try another one. Mapping a machine name to an IP address is the first step toward getting a connection to the machine. Let's see, who hasn't gone? Beatrice.
True.
Yeah, that is true. That is true. Let's look at 24. Multiple autonomous processors simultaneously executing different instructions on different data. MIMD architectures include multi-core superscalar processors with distributed systems using either one shared memory space or a distributed memory space. What on earth does that mean? That sounds so complicated. I better get a student to tell me. Let's see, who hasn't gone yet? Caroline, what do you think?
That's true.
Yes, it is. It's true. MIMD. So multiple autonomous processors. That's like CUDA cores. Bunch of CUDA cores. Okay, now we're getting into the semiconductor device fabrication stuff. Advanced topic. So it's NAND memory, and there are several transistors. Here they are, and they are connected in series, and the bit line is pulled low only if all the word lines are pulled high. So what do we got here? This is looking an awful lot like a field effect transistor with a floating gate right in through here that's storing the data. And so what's the question? True or false? True or false? Let's see. Who hasn't gone yet? Daphne, I think we're up next.
I think this is false.
Yeah, so actually that is true. What happens here is NAND memory actually has to be written in such a way that you connect all the transistors in series, just as you see here, and then you have a bit line coming in here to select the transistor. So, in fact, it is true. Let's see, what else do we have here? A member inner class is a nested class defined within a method. And who can we call on next? Gilliam.
That is false.
Yeah, that's correct. If you have a nested reference data type defined within a method, that's an inner class, but it's inside the method. It's not a member inner class. Member inner classes would be inside of a class, but not inside of a method within the class. Let's look at the proxy. A proxy is a service that manages connections between the intranet and the internet. The internet and the intranet. Jacob, what do you think of that one?
True.
That is true. So what is the difference between the intranet and the internet?
Internal, external.
Yeah, that's right. So if I have, we'll go back to my little console over here. These IP addresses are non-routable addresses that are all inside of the 192.168.1 root. So I can ping my router at 192.168.1.1. And in order to be able to save, in other words, we can exhaust the total number of IP version 4 addresses available. What we do is we go to a router that has network address translation, or NAT, and they give us non-routable IP addresses. Externally, our IP address is different, right? So in other words, if I go to website and they say, what's my IP address? This is my IP address from the outside world. So that's outside of my cable modem. And if I had my cable modem configured so it port mapped port 80 to my local web server, then in fact it would map from this external address to an IP address 192.168.1. something. And so then all of the port 80 traffic would go to that machine. And that would be how the web server is found by the outside world. And I'd have to map using a domain name server and probably something like docjava.com, have to map that to this IP address so that all the traffic would go there. So in NOR memory, you can erase any single bit. Any single bit. So let's see, what do we got here? So here's NOR memory on the left versus NAND memory on the right. So this is like the difference between double EEPROM and flash on in an Arduino. Two different styles of memory. And so the question is, in NOR memory, can you erase any bit? Any bit? Well, look over here. These transistors are all in series. And these are not. These are not on the left, and it's NOR memory on the left. So NOR memory, can you erase any bit? Let's look at Jorge, have you been going? I'm going to call on you just because I don't think we've heard from you yet. No? And Jacob, how about you? What do you think? Is that true or false?
I'm gonna say true.
Because you can see the structure of these things. We can address any given transistor, whereas here we have to go through a whole bank at a time. OSI. OSI is an acronym for, what do you think, John?
Open Systems Interconnection.
Yep. Yep. That is true. Let's see. Routing is a service reserved for the transport layer. Jorge, are you with us? All right, let's see who's next. Kristen.
False.
Yeah, that's false. What layer has routing in it? Kristen.
I don't remember. Does
Yeah,
it
so
start with an A?
No, it's the network layer that does the routing. So we have I need something to write on. Listen, where can I write this? Oh, here we go. So right, there's the physical layer. Whoops, something happened. I don't know why this isn't working. It won't let me type. It's very unusual behavior. Permission denied. Where am I? Oh, I'm in Etsy. That's why it won't let me do it. Yeah. You have to be a super user to start writing in Etsy, which is good actually, because you don't really want to start making random files there for no reason. So you have 7 layers, just like the 7 dwarfs. The physical layer, the data link layer, the network layer, the transport layer, the session layer, the presentation layer, and the application layer. Is that 7? 1, 2, 3, 4, 5, 6, 7. Yep, that's 7. So here's where you get the bits. And here's where you have data link protocol units, also known as packets. This is where you have internet protocol. Here's where you have transmission control protocol. So if you put it on top of IP, you have TCP/IP. But you don't have to have that. You can also have multicast, which would be user datagram protocol. Oops, protocol. In which case you would have UDP IP. Then comes the session layer. That's where you can have things like HTTPS, secure sockets. Then comes presentation layer. That's the hypertext transfer protocol, common object resource broker administration, remote method invocation. I don't know what else. Can't think. Oh, maybe some other protocol, perhaps file transfer protocol, etc. And then this is where your browser hangs out. So these are your applications, things like that. So the 7-layer paradigm is alive and well. And that's how I would classify the different layers that you're used to. And you can see how they all have different roles. Right? This one might, if you wanted to support triple DES encryption, which might be useful if you wanted to do something like secure shell. And certainly we know why TCP/IP is important, because that gives us sockets and streams. They are unformatted sequences of bytes, but we start to get some formatting when we go to the higher layers. And you don't get routing in the transport layer. That transport control protocol is used for flow control. So OSI reference model has, let's see, LAM. How many layers do you think the OSI?
It has 7 layers.
7 layers. Yes, we just did that. So that was kind of a gimme, I guess. Hey, look at this. We've gotten through 32 questions already. We're doing pretty good here. Let me just look at my calendar and sort of see what's going on with the rest of this. You know, we have a class on Monday, and we've got a class on Thursday. So there's still 2 more classes to go. I have a feeling we're going to knock this whole final off at this rate. I mean, we're going like gangbusters through this thing fast. I'm going to have to make the test longer. Now it's beginning to sound serious. We'll have to make it longer. So let's see. Which layer provides the user interface? The user interface. Let's see. Rakibul. Rakibul, did you go? Ricky. Ricky Shaguru?
Yep, sorry about that. It's the application layer.
That's correct. That is correct. Let's go to question 33. On the internet, multicast packets need to be forwarded by routers. On the internet, they need to be forwarded by routers. Why do they need to be? Do routers have to do this? They need to be forwarded? I don't know what that means, need to be. Shamrock, what do you think?
This seems true.
Yeah, it seems more true than false. It depends how you interpret it. Routers don't really need to forward these things, but if they don't, then they won't get through. So if you want them to get through, then yeah, they need to be forwarded. But if you don't want them to get through, then no, they don't need to be forwarded. And in fact, routers certainly don't have to forward them. So this need to be forwarded. That sounds a little confusing. You know what I think is I'll reword that a little bit to make it clear. So CR346, I'm going to revisit this question 33 just because I don't like the way it sounds. It's too ambiguous. Need to be forwarded by routers. I guess in order to be seen would be the end of that sentence. Question 34. Stephanie, request for comments is often used for specifications. Does that sound true?
I think that's true.
Yes, it is. That is exactly right. You guys are doing great. So this is good. You seem to have been a lot of learning going on here, and that's very good. Very good. So how do you feel about this? About the final? Does this seem pretty good to you guys, or the format's all right? Could have done a project, I guess.
Professor,
Yes.
could you do question 57?
Yes, I could, but we've got 2 classes to go, and we seem to be doing roughly one question. Well, I think we're going to get to we're going to get through this whole thing with 2 more lectures. So if we go sequentially, would that be all right instead of jumping around? Because
Yeah.
I think we're going to get there. We're going to get there. I don't know if well, let's see. I'll do a rough computation. We just did 34 questions in 60 minutes. So we're doing roughly 1 question every 56 seconds. No, that can't be right. Go the other way. Hello. So 60 minutes divided by 34 questions. It's taking 1.7 minutes per question. So if I multiply that by 100 questions, that's 176 minutes. And then if I divide through by 60 minutes in an hour, that's 3 hours. And we're going to have another 2.5 hours. We'll have nearly 3 hours to get through this test. So I have a feeling we're going to get through 80 or 90% of this test. Just by going sequentially. If we keep the schedule. You know, you guys, you have to keep participating here. That's important. Such as it is, I mean. So let's see. The original SIMD idea came from Alan Turing's paper in 1946. You know, that's a good question. Let's see. Angelica, do you know the answer to that question?
Is it true?
It is true. It is true. And I think it's interesting, you know, and it might be a worthwhile paper to read. So I wonder if it makes sense to sort of take a moment and just kind of examine. Whoops. What did I just do? Blackboard overrode my Firefox. Wow. I tried to make a new window in Blackboard. Okay, sorry. Let's not do that. I was going to Google it real quick, but Blackboard had other ideas. SysD, a single instruction, single data. Where can I find SysD? SysD, Avery. Where's the SysD?
Arduino Uno or Intel Pentium. Oh, sorry, I don't know how to pronounce it.
Pentium. Yeah, you were right. That's exactly right. The Pentium 4. Yeah. Single instruction, single data. It's a single stream. Actually, many microcontrollers do this still. Question 37. If a port is already being used, a server programmer need not find a free port for his or her service. Bashir, what do you think?
True, I guess.
Well, it's already in use. So what you get when you try to open up a port that's in use is you get a port in use exception at runtime. So if you have a web server, it's running on port 80, and you try to listen to port 80 in order to create your service, then you're going to get that port in use exception at runtime, and it will not work. So ports are consumed resources. And once a port's used, you do not get an opportunity to reuse it until you shut down the program that's using it. It's like trying to use a COM port. If I have a program that has a COM port open, then if another program tries to open the same COM port, it gets an error. You can't have two programs writing to the same serial port at the same time because that would create corrupted data. It's the same thing as if you had two files opened by the same program for write at the same time. You couldn't do that without corrupting the data, because if two programs are starting to write to the same file at the same time, you know that's going to be chaos. Let's do SMTP is an acronym for Beatrice, what do you think?
Simple mail transfer protocol.
That's exactly right. Thank you. That's exactly right. And let's see now. Question 39. What is needed when communicating using sockets? Caroline, what do you think you need?
All of the above, like port number and IP address.
Yep. Yep. You got to have that. You got to have it. Let's see what we got next. What is the role of a server socket Daphne? Daphne, are you with us?
Yes, I'm here. Sorry.
That's all right.
Is it to provide a communication?
Yep, that's exactly right. Server sockets give you a communication endpoint used for listening to listen for a connection request. That's exactly right. I got a quick demo here, which we can use to try and illustrate this. So here's an Arduino with an Ethernet shield, and it's running a web server. I just had to turn it on just now because I had it off. And if you look at this web server, it's listening to an IP address. And if you look at it here, it's starting up a server socket on port 80. And if you go, this is where I'm going to end up eating my words because this might not work, but we'll try it anyway. So if you go to 192.168.1.77, there it is. It's the Arduino. and you can tell it to increment or decrement a position of a servo. And then you can give it a new position. It's generating the web page, and you can hit submit. And then that moves the servo by 67 degrees. So that's all being generated locally by the little 8-bit toaster controller that is the Arduino. Hard to believe, right, that it can do that, but you don't need much to start a server socket. And in fact, if you look at the entire program, it's a really small program. And what it's doing, this is kind of interesting actually, is it's going to the client and emitting the HTTP protocol with HTML embedded. So it's outputting HTML, and it's also outputting data. So you can get the analog channel, and you can do all these different interesting things. This one's a sensor read. This is not the same program I'm writing. The one I was doing was web-based servo. That's the one I was doing. The sensor read, this guy is going to actually read the sensors coming in. So if I run this program, oh, I have to make sure it can upload. And there it goes. Let's see what happens when we refresh. And there it is. It's telling me what the values are for the analog input. And I've got 6 ADD converters, and it's refreshing as I go. So that's cool. Different program gave me a different result, reading in the ADD converters. The other one was operating the servo. You could operate stepper motors. In fact, what's interesting is you could go and map this port 80 out using your router to the internet, and then people outside of the internet could gain access to your networked embedded system, whatever it might be and whatever it might do. It's not clear, but there you go. So a nice example of running server sockets. Everyone should take the embedded microcontrollers course. We used to call it EE346 and 346L, but I think it's got new numbers now and I can never remember them. ENGR something 346. I can't remember. New numbers. What are you going to do? People like those numbers, right? You like those numbers. I hate them. But oh well, life in the big city. So let's try number 41. SMTP servers appear on port. Let's see. Who hasn't gone yet? Gilliam, I think you're up.
25.
Yes, that is correct. That is correct. Let's go to the next one. What is multi-threading? Geez, these questions are easy. Huh, boy. Jacob, what do you think? What is multi-threading?
I think it's two different processes run simultaneously.
Oh, it's having more than one thread in a single task. A process is different from a thread. So you could have multiple threads running in a single process. So when we think about a multitasking operating system, we're thinking about a multi-process operating system. So when I go to my activity monitor, I'm seeing a lot of different processes. Right? But when I look at my little Java program running this display and updating it, well, that's a thread, a separate thread running inside of the Java program, which is running as a process in the Java virtual machine. So the Java virtual machine, which you can see right there, is actually a process. And there it is. And it's showing you different windows that are open. These different windows are shown on a different monitor. So that's a thread. And multi-threading means having multiple threads in a single task. Now, here comes question. How are we doing for time? 5 minutes? That's good. That's good. We get a lot done here. We're almost halfway through. Look at that. What is the name of the method used to start a thread's execution? Let's see. John.
Is it init?
No, it's not. Jacob, what do you think?
I think run.
Run. Well, run will actually get it ready to run. Oh, no, run. No, I'm sorry. Start. Start will get it ready to run. Run.
Isn't it
It's
start?
going to. Sorry?
Isn't it start?
Start will get it ready to run, but run is the thing that's invoked. So start doesn't actually start the execution of the thread. What it does is it queues it into the thread scheduler. And then the thread scheduler finds it to be ready to run, but the thread scheduler must invoke the run method. So what happens is you you create a method, you create a new thread, and the argument to the constructor is a class which has implemented the runnable interface. And the runnable interface has one method in it, and that is to run. And so then when you take a thread and you make a new instance of a thread, it is not ready to run until you hit start. That proceeds to queue the thread, making it ready to run, but it will not run until the thread scheduler allocates resources to it, and then it invokes the run method. So that's how that works. So you need, if you want the thread to execute, you have to invoke the run method or have it so that it's ready to run and wait for the thread scheduler to invoke the run method for you.
Professor, we did this question on a past homework and the answer for that was start.
Yeah, let me check. Oh, you're correct. You're correct. I'm going to review that one. That's question 43. Yeah, maybe there's a bug in here, because if you think about it, is it really going to start the thread's execution? I don't think so. I don't think it starts until the thread scheduler invokes the run method. So it's not actually executing when you hit start, but I can understand why you would say start. And I see that it does say start in the answer key. So this is looking more and more like a bug in the question, but I will review it and we will get back to it. And on that note, it's 3:13. So we've got bugs in questions 33 and 43. So quality control will review these and make sure we have things squared away for next time. So enjoy the weekend, stay safe, and thank you for your attentions.
Thank you, Professor.
Thank you.
Thank you, Professor.
You. Thank you.
Thank you.